Welcome to One Chemistry. We are seeing many organic concepts. In this video, we are going to see Wittig olefination reaction. It's an important reaction, basically a functional group conversion reaction. You are converting ketone into alkene. The video will be very detailed with 29 fully solved examples. It will give very good perspective on olefination reaction. Stay tuned. What is inside this video? At first, we will see what is Wittig olefination reaction, then mechanism behind the reaction, then basics. Basics include Ylide and its stability and stereoselectivity of the olefination, whether it is E or Z, then notes on the starting material, how starting material can influence the product, then competition between inter and intramolecular reaction. It will be very detailed. Then very important part of the video, we solved almost 29 problems with complete description and detail. These are all from various examinations to help you to master the concept. At first, we will see what is Wittig reaction. It is technically called Wittig olefination reaction. The reaction converts carbonyl group into CH2CH2, basically CO into alkene by the use of Ylide. The Ylide is Phosphonium Ylide. We will see Ylide very detailedly with a side product of phosphine oxide. The name Wittig comes from the scientist. He is the Nobel laureate in the synthetic chemistry. The reaction has much prominence because of new CZ bond. The facts about the reaction is it's a functional group conversion with one step up, meaning one carbon more. Then the alkene can be tuned based on Ylide stability, then stereoselectivity, either E or Z form, not the mixer. It's highly selective. So all three facts dictate the reaction. Then one key point to remember, Wittig reaction basically conversion of ketone into alkene. It is easy to remember because it is the reverse of ozonolysis reaction. Ozonolysis converts alkene into carbonyl. In Wittig reaction, carbonyl into alkene. Basically, Wittig reaction and ozonolysis are opposite to each other. Then we will see what is Ylide. Here phosphorus Ylide we are using where positive charge and negative charge nearby which stabilize each other. It can be denoted as salt or a double bond. Phosphorus hold the positive charge, carbon hold the negative charge. So it can be a double bond or charge separated each other. So the Ylide and its preparation is important because it's a one of the starting material. The preparation is phosphine reacts with methyl halide, then substitution happens. Phosphine substitute the halide, which holds the positive charge because you are increasing the valency. The counterion will be anion, which is halogen, here not shown. Then beta lithium you are using mean beta lithium abstract the proton, you end up with negative charge. Positive charge and negative charge can be written as double bond or the charges. It is called Ylide. The Ylide may look simple. Technically, if you see, it has three phenyl system and one positive charge on phosphorus and side carbon you have CH2. Technically, it's a bulky molecule with phosphine. So you should learn the Ylide upside down. We will see all the concepts related to Ylide to help you to solve the Wittig reaction. We will see the basic, which is mechanism behind the reaction. Technically, you can write it in many ways. Different books suggest different mechanism. Here I shown concerted 2 plus 2 cycloaddition. Carbonyl and phosphine has double bond. So both can form the cyclized structure. How it is possible mean carbonyl hold the positive charge, Ylide hold the negative charge. So two carbons can interact. In above case, phosphine has high affinity towards oxygen, which form four-member intermediate, which is called oxyphosphatane or betaine. The four-member ring is highly strandful because of the ring size. It form phosphine oxide and alkene. It's a desired product. Obvious question you will get it. Whether the alkene is E or Z. Next, we will see the Ylide stability. Ylide holds the negative charge. It can be stabilized or destabilized. If you want to stabilize the Ylide, you should add electron withdrawing group, basically nitro, cyanide and carbonyl. If you want to destabilize the Ylide, you have to add electron donating group, for example methyl or the lone pair atoms. Anything can destabilize Ylide. Here why we are discussing alignment, because Ylide stability crucial for the alkene formation, which is our product. We should see whether it is E or Z. Through the Ylide stability, we can see whether E alkene or Z alkene will form, basically a stereoselectivity decided by Ylide stability. Let us discuss the stereoselectivity. Suppose you have unstable alignment. Is it stereochemistry observed? Because unstabilized intermediate means the lifetime is less. So quickly form the product, which is kinetic product, cis product. First carbon attacks, it will rearrange itself as much as quickly. So it combines, you end up with kinetic cis product through the same four-member mechanism. So end isomer is Z isomer. You can call cis isomer. The whole process is kinetic, very quick because of unstabilized line. Now let us see the stable Ylide, which form E stereochemistry, meaning the intermediate is more stable, so it will rearrange itself to form less steric product, which is trans product. R1 and R2 will be further away, which is trans product. It will form same four-member ring. Then the intermediate converted into E isomer. So stable Ylide produce the E isomer. Stable Ylide is the thermodynamic product, always end up with stable E isomer. Here, to find the stereochemistry, you need not to write the mechanism. Better analyze the Ylide stability. Here, if you look at the carbon substitution at the Ylide, you can find the product. If it is electron withdrawing group, anion is stable, reactivity is less, it forms stable thermodynamic E product, that is E alkene, or you can say trans alkene. If the system is electron donating mean anion stability is low, alkene is very reactive, it forms Z alkene, which is kinetic product. So stability leads to the E product and stability leads to the Z product. So you should memorize electron withdrawing E product, electron donating Z product. You can memorize this very easily through the acronym words VEDZ. Withdrawing mean E, donating mean Z. So words. Then the important basic is intra versus intermolecular reaction. Wittig reaction can be inter or intra. Here I shown the starting material, which is linear chain product, one side carbonate, other side Ylide. So Wittig reaction is possible. Whether it is reacts itself or reacts outside is the real question. Reacts itself mean form cyclic product. Reacts with self mean it form larger linear product. Here intramolecular, that is reaction within, is possible because it don't require any collision. So intramolecular reaction is highly favorable rather than intermolecular. Then the important basic, which is notes on starting material. The starting material can be anything, need not to be only with carbonyl. You can start from heating, which is cumulative double bond, end up with alkene, or isocyanate, end up with alkene, or nitroso, end up with alkene, or even imine, end up with alkene. So all starting materials are possible, end up with alkene. So the scope of Wittig reaction is high, stereochemistry is good. That's why it is very important naming reaction. Then we are going to see the important section, which is fully solved examples from various examination. We discuss almost 29 examples. Why so many means problems are best way to learn. It will give different perspective, complete understanding and problem solving skill. So make use of it. First example is linear chain compound with ketone at one end, bromine at another end. You are using phosphine and butyl lithium. You should find what will be the final product. By looking at the phosphine, you might realize it's a Wittig olefination reaction. First step will be Ylide formation. For that, you should redraw the molecule with bromine and carbonyl nearby. Then only the reaction will be easy to understand. So first step will be phosphine attacks the bromine carbon. Attacks leads to the bromine elimination and PPH3 substitution. So phosphine gain more valency. That's why positive charge. Then if you use butyl lithium is the strong base. Abstract the proton, form the Ylide. Ylide negative charge is important because it is going to attack the carbonyl. It attacks, it form the four-member ring. Here for the simplicity, I shown only carbon-carbon bond. Then PH3BO elimination leads to the alkene there. So you start with linear compound, end up with cyclic compound. Cyclic compounds are more stable, always form. Further, intramolecular is more possible than the intramolecular. That's why we end up with intramolecular Wittig reaction. The concept you have to learn here is you should master the Ylide formation to master the Wittig reaction. Then the next reaction, you have acetophenone reacting with phosphorus halide with ester substitution. You should find what will be the final product. Here Ylide is there, Carbonyl is there, so Wittig reaction. But Ylide here is the stable Ylide. Why? Because anion attached with COOMe. CO is electron withdrawing 2,2sp2 carbon. So it is the stable Ylide. So we redraw the starting material with charges phosphine positive, carbon negative. Carbon is the nucleophile. It attacks the carbonyl. You have new CC bond. So the attack happened. You have phosphine and oxygens are nearby, which is very attractive and affinity. So phosphorus oxygen bond forms. Finally, phosphine oxide eliminates. You end up with alkene. Here, Ylide is the stable Ylide. So you end up with E alkene there. The concept you have to learn here is whenever you have stable Ylide, you end up with stable thermodynamic E alkene as the final product. Then the next reaction. Here you have linear compound with two carbonyl. One is ketone, another is ester. You are reacting with phosphine with CHCH3. You should find what will be the final product. Here phosphine is there, two carbonyl is there, definitely Wittig reaction. But which carbonyl reacts or which functional group reacts is the real question. If you look at it, ketone and ester. Ester is less reactive because of OET. It can donate the electron, weaken the positive charge. So ketone is more reactive than ester. You end up with CC bond on the carbonyl ketone, not on the carbonyl ester. So two attacks possible. A attack leads to the ketone. B attacks leads to the ester. A is major because it is ketone. Then phosphine oxide elimination. You end up with final product. The concept you have to learn here is in Wittig reaction, reactivity of the carbonyl decides the functional group reactivity. Then the next reaction. Starting material is the benzyl alcohol. Product is styrene with acid. You should find how you can carry out the reaction with various reagents, various pathways. So you should do organic conversion with one carbon more with alkene. Also OH to COOH. Here starting material is the benzyl alcohol. You need double bond there. For that you should convert it into carbonyl. So we should use PCC. PCC is pyridinium chlorochromate, controlled mild oxidation agent. converts alcohol into carbonyl. Then if you use stable Ylide, which is ester attached with phosphorus Ylide, it can undergo Wittig reaction with ester. Then if you do acidic or basic hydrolysis, you end up with acid there. Here stable Ylide you are using, so you end up with E configuration or trans configuration. So stereochemistry and conversion matter here. The concept you have to learn here is Wittig reaction can be a part of larger organic conversion reaction. Then the next reaction, you have benzaldehyde, benzene you are using, and phosphine ylide as a reactant. You should find what will be the final product. Here phosphorus ylide you are using. If you redraw the molecule with charges and proper orientation, reaction will be easy. Here attacking species is nucleophile, which is carbon negative charge. So we bring it as a reaction center, carbon side chain. So we attack the carbonyl. So you have new CC bond with phosphine elimination. You end up with alkene. It's a simple Wittig reaction, but stereochemistry matters. Here anion is there. Methyl groups are electron donating group. Weaken the negative charge or destabilize the negative charge. End up with unstable Ylide. Unstable Ylide always form kinetic product, which is Z alkene. Here you end up with Z alkene. So final product is cis-like product. So the concept you have to learn here is you always look for the Ylide stability for the stereo selectivity. Then the next reaction, here you have cyclohexadiene. You are using phosphonium ylide, heating it up. Here lithium salt of substituted amine and formaldehyde. You should find what will be the final product. Here diene as the starting material. Phosphorus positive charge in alkene make it as the dienophile. So diene and dienophile in the heating condition mean Diels-Alder reaction. So you have 4 plus 2 cycloaddition form the phosphine compound there. Then next step you are using lithium salt of amine. It's a strong base. It abstract the proton form the Ylide there. The Ylide is there. You are using the formaldehyde. So it has carbonyl. So Wittig reaction is possible. So negative charge attacks the carbonyl. You end up with alkene there. You start with monocyclic compound, end up with bicyclic compound. The concept you have to learn here is while doing Wittig reaction, you should also master the other naming reaction like Diels-Alder reaction. Then the next reaction, you have cyclohexanone. Alpha position, you have methyl group. Phosphorus ylide you are using. We should find whether the product is E alkene or Z alkene. Here phosphorus ylide you are using. We should redraw the molecule with charges. Carbon has negative charge, phosphorus has positive charge. The negative charge attached with the electron donating group, which is methyl group. So it's unstable ylide, probably form Z alkene. So first step will be anion attacks the carbonyl. So nucleophilic addition reaction, new CC bond, then phosphine oxide eliminates, you end up with alkene. Here alkene is Z alkene because Ylide is unstable. The concept you have to learn here is if Ylide come with substitution, you should be very careful about stereochemistry. Then the next question, starting material is the linear compound with 2 carbonyl and phosphorus oxide. You are using sodium hydride as the reactant. You are using sodium hydride as the reagent. You should find what will be the final product. Here phosphine and carbonyl in the same chain mean intravittic reaction is possible. You are using sodium hydride. It's a base. It abstracts the proton. Weaker proton is in between carbonyl and phosphorus. So it removed, it formed Ylide. The Ylide and Carbonyl are away. If you redraw the molecule, it will be favorable for Wittig reaction. So if you redraw carbonyl and phosphorus Ylide nearby, the negative nucleophile attacks the carbonyl. You have new CC bond. Then phosphine oxide elimination, you end up with cyclic product. The cyclization and intramolecular nature driven the final product. Additional factor promote the elimination is conjugation. The concept you outline here is always intramolecular product forms because no collision is required. Then the next example. Here you have cyclohexanone. In alpha position you have side chain with bromine. You are using phosphine and sulfoxy compound with CH minus. You should find what will be the final product. Here first step will be Ylide generation. For that phosphine attack bromine carbon. Bromine replaced with PBH3. So positive charge is there. Then the CH minus from sulfoxide abstract the proton. It will be like base. Base abstracted. You have Ylide formation. Ylide and carbonyl in the same compound. So intramolecular Wittig reaction. As we discussed, intra is more favorable than inter because it don't require any collision. So negative charge attack the carbonyl. You have new CC bond, then phosphine and oxygen nearby, both remove. You got alkene. You start from monocycle. You end up with fused compound. The concept you outlined here is intramolecular Wittig reaction is more favorable than intermolecular reaction. Then the next example. Here you have alpha hydroxybenzaldehyde. We are using sodium hydride and phosphine with bromine salt. You should find what will be the final product. Here alcohol is there. You are using the base. Base abstract the proton. It creates O nucleophile. O nucleophile can attack the alkene through SN1 prime mechanism. O minus attacks the terminal carbon of the alkene. It forms Ylide. It's a one way to generate the Ylide. Ylide form inside the system. As we discussed already, intramolecular Ylide reaction is possible. Negative charge attack the carbonyl. You have O minus with ring formation. If you redraw nicely, you have new 6-member ring formation with phosphine and oxide. Here phosphine can take the oxygen, end up with phosphine oxide elimination. The final product is alkene there. You start from side chain, end up with fused compound. The concept you outlined here is you have to master the Ylide formation to master the Wittig reaction. Then the next reaction, you have cyclohexane with epoxide. You are using lithium salt of Ylide and aldehyde. You should find what will be the final product. Here epoxide is the lithium salt you are using. It can be like nucleophile. It can open the ring. The addition will be trans addition because SN2 reaction demand diaxial position. You end up with O lithium and Ylide transposition. If you redraw nicely, you have trans OH and Ylide. Ylide is there. You are using the aldehyde. So chances of Wittig reaction. So alkene form with butyl side chain. You end up with final product. Here the concept you outline here, while solving the Wittig reaction problem, you should master the relative basics. Here, SN2 reaction required diaxial position. Then the next example, here you have cyclohexenone, which is alpha, beta and saturated ketone. Alpha position you have aldehyde. Then phosphorus Ylide you are using with ester side chain. Vinyl ethyl ether you are using, heating it up. You should find what will be the final product. Here the chemoselectivity is the real question because you have two carbonyl group, one Ylide. Which carbonyl reacts is the real question. One is aldehyde, one is ketone. When compare the reactivity, aldehyde is more reactive than ketone. So aldehyde carbonyl get involved. So carbon attacks the carbonyl. you end up with new CC bond. So finally you end up with alkene there. The alkene is conjugated diene. So chances of Diels-Alder reaction, because heating condition you are using, you have one diene and dienophile. So chances of Diels-Alder reaction. So if you do 4 plus 2 cycloaddition, it is the asymmetric alkene. You end up with ortho substituted same planar product, because cycloaddition is in addition. So both should be on same plane but below the plane to avoid the steric effect. Here many factors involved. One is you should decide which carbonyl reacts. Second, which alkene formed dominantly, whether E alkene or Z alkene, and it is above the plane or below the plane. So three different selectivity. You should judge and find the final product. Then the next example, here you have benzaldehyde. You are using phosphorus Ylide with O-methyl group, then acidic hydrolysis. You should find what will be the final product. Here the reaction is simple and straightforward. Carbonyl is there, Ylide is there, so Wittig reaction. So the first step will be negative charge attacks the carbonyl. You have new CC bond. Then phosphine and oxide nearby. So it form 4-member cyclic intermediate structure. Phosphine and oxygen affinity is more. So it leaves us a phosphine oxide, end up with alkene there. Then further you are doing acidic hydrolysis, which converts OCH3 into OH. Here the OH attached with alkene, it is the enol. So technically hetoenol tautomerism possible. You end up with aldehyde there. So the concept you outlined here is, in Wittig reaction, terminal product can be tunable by the choice of reagent, nature of the reacting species. Then the next example, here you have benzene, para position you have methoxide and aldehyde, ortho to aldehyde you have O ether with alkene side chain. You are using phosphorus Ylide, then heating it up. You should find what will be the final product. Here the reaction has many functional groups, so many possibilities. We will go by one. The reaction involved two types of Claisen rearrangement and one Wittig reaction. Since our focus is Wittig reaction, we will see others quickly. First, we will arrange the reactants for the Wittig reaction. So phosphorus Ylide you are using, end up with alkene there with ester side chain. Side chain alkene can undergo Claisen rearrangement because alkenes at the terminal. If you rearrange nicely, you end up with carbonyl. Then again rearrangement happen. You end up with aromaticity, para position alkene, and you have alcohol. Since alcohol and ester can form the lactone, the acidic hydrolysis and ring closure leads to the unusual product. The reaction may look complicated, but the fact you have to know here is naming reactions are crucial for organic conversion as well as total synthesis. Then the next example, here you have epoxide, both ends you have methyl, methoxide, hydrogen and methyl. Two methyls are in trans relationship, one methyl and methoxide in cis relationship. Here lithium phosphine you are using methyl iodide as the reagent. You should find what will be the final product. Here epoxide is there. Epoxide is a strain system. It always try to open itself. Lithium assists the ring opening. Then phosphine, the counterion, can attack the ring. Phosphine attack from less hindered side because the reaction is SN2 reaction. Always prefer backside attack which need less steric position. Then phosphine attacks ring open. You have the chances of indirect Wittig reaction. So phosphine oxide in the same system. So ring rotate to meet the phosphorus oxygen nearby, which makes the configuration reverse. So you rotate it, then methyl attacks the phosphine, make it as a good leaving group. So phosphine oxide leave, you end up with E alkene. Here the concept you outlined here is, while the ring opening, you should always analyze the possibility because here phosphine and oxygen should be on same plane, or you can say syn plane. Since the rotation is mandatory, the configuration of carbon atom changes. So always watch the stereochemistry while doing Wittig reaction. Then the next reaction, you have cyclohexenone, which is alpha, beta, unsaturated ketone. In fifth position, you have dimethyl group, phosphine, TBDMS chloride you are using, N-butyl lithium, butanate, and DBAF you are using. You should find what will be the final product. Here you have alpha, beta, and saturated ketone. So chances of Michael addition. For that you should analyze the nucleophile, which is soft or hard. Phosphine is the big molecule, so it attacks, charge travels. You have new CP bond. Here hydrogen is weak because of phosphine positive charge. It can be removed by butyl lithium, form Ylide. So chances of Wittig reaction. Ylide form attacks the carbonyl. So carbonyl attacks new CC bond. Phosphine and oxide in the same plane. It eliminates. You have alkene there. Then DBDMS eliminates. You end up with conjugated ketone. The concept you have to learn here is phosphine is the soft nucleophile. It will undergo Michael addition reaction. Then the next reaction, you have cyclohexenone, which is alpha, beta, unsaturated ketone. You are using ethyl magnesium bromide, chromium oxide, dichloromethane, and phosphenylide. You should find what will be the final product. Here ethyl magnesium bromide you are using, conjugated ketone is there. Since ethyl is the hard nucleophile, since it is generated from magnesium, it attacks 1-2 position. So second position ethyl attacks, O minus it forms, then proton abstracted, you have OH bond. Here chromium oxide you are using, chromium oxide undergo sigmatropic rearrangement reaction. The position of OH changes, you end up with different conjugated ketone. Then Wittig reaction you apply because phosphine Ylide is the reagent. You end up with alkene. The starting material and products are completely reversed. You end up with completely different product. Then the next reaction. Here you have ketone. One side you have phenyl. Another side you have aldehyde. You are using phosphorus Ylide with ester substitution. You should find what will be the final product. The question is all about chemoselectivity because phosphorus Ylide you are using, but two carbonyls are there. One is ketone, one is aldehyde. So the question is about chemoselectivity. Aldehyde is more reactive than ketone. It involves the Wittig reaction. So phosphine attacks the aldehyde carbonyl. It forms new CC bond. Then phosphine oxide elimination leads to the alkene there. Here you may wonder which alkene will form, E alkene or Z alkene. The E alkene is favorable because of stable Ylide. The negative charge on the carbon stabilized by carbonyl group withdrawing ability. So Ylide is stable, alkene is E alkene. The concept you have to learn here is this kind of questions may come combination of chemoselectivity and stereoselectivity. Then the next example, here you have cyclohexanone, alpha position you have 2 methyl group. You are using phosphorus oxide with ester substitution, sodium hydride, lithium aluminum hydride, D minus DET and peracid with titanium isopropoxide you are using. You should find what will be the final product. This question is a kind of tricky question. Why? Because the concepts involve stereoselectivity as well as diastereoselectivity because it involves Wittig reaction and SAR plus epoxidation. First step will be Ylide formation and attack of carbonyl. So Ylide forms with a strong base. It attacks the carbonyl. You have new CC bond. Then phosphine oxygen eliminates. You have alkene there. You may wonder which alkene will form. Alkene is E alkene because anion connected with carbonyl group of ester, which is electron withdrawing, stabilize the anion, end up with E alkene. So stereoselectivity achieved here. Then lithium aluminum hydride you are using, which converts ester into alcohol. the alcohol above the plane. The alcohol is vertical, left side. So same plane epoxide happen. So above the plane epoxidation occur. You end up with final product. The concept you outline here is stereochemistry, and the naming reaction based on stereochemistry are highly important, which can decide the bigger molecule stereochemistry. Then the next reaction. Here you have cyclohexanone fused with 4 member, 5 member, 3 connected methyl group. Further you are using tosyl acid. You should find what will be the final product. Here alkene is there, Ylide you are using. So straightforward you write the alkene there because Ylide carbonyl combined form Wittig product with phosphine elimination. So CO becomes CH2 at first step, then H plus attacks. H plus is the electrophile, form the stable cation. So only add to A, generate the tertiary cation. It forms, since the ring is strainful, one of the ring which is 4 member ring is strainful, it open itself, form the 5 member, one side ring contraction, another side ring expansion. So I give a numbering for the reaction. So fused system happen, you end up with alkene there. The concept you have to learn here is strain in the system always relieve if the intermediate is the cation. More or like the reaction involve Wittig reaction as well as Wagner-Merwin rearrangement. Then the next reaction, you have benzene, alcohol and CHO in ortho relationship. Here you have dibromoalkane, phosphine, sodium hydride you are using. You should find what will be the final product. Here bromine is there, phosphine you are using in Ylide formation. For the Ylide formation, phosphine attacks the carbon with bromine. It form phosphine cation, then sodium hydride abstract the proton. You have Ylide there. Ylide is there. Carbonyl as the starting material mean you have new CC bond. So carbonyl to alkene conversion happen. But side chain you have bromine. So bromine and alcohols are nearby. So oxygen can act as a nucleophile, involve the ring closure with bromine elimination. This reaction, the intramolecular reaction, which is more favorable because it don't require any collision. So starting material to product completely rearrange fused product. The concept you outline here is you should master phosphine chemistry to master the Wittig reaction. Then the next reaction, here you have amide, one side you have acetate, another side you have conjugated aldehyde. You are using phosphine Ylide with ester, lithium aluminum hydride and acidic hydrolysis you are using. You should find what will be the final product. The molecule has many functional group, amide, ester, aldehyde, alkene. So chances of many reaction, many possibility. Our focus is Wittig reaction. So first we carry out the Wittig reaction with Ylide. You form alkene there. The alkene is conjugated alkene. Amide you have in the system. So chances of similar like Diels-Alder reaction. So the addition and fusion happen. You end up with new cycle. If you read that nicely, you end up with 6 member and 5 member ring with nitrogen as the connected atom. The whole reaction may look different, but the real question is about chemoselectivity. Whether aldehyde reacts or ester reacts or amide reacts, aldehyde carbonyl is more reactive. It forms Wittig reaction. Then the next reaction. Here you have hexane with conjugated double bond, light, ozone, methyl sulfide and phosphine Ylide with ester you are using. You should find what will be the final product. Here by looking at the diene, you might realize the chances of pericyclic reaction in the light condition. So if you redraw nicely, you have butadiene like architecture. Light reacts mean you end up with cyclobutene. If you are interested, go and study pericyclic reaction differently. It's a kind of vast chemistry we cannot teach here because it is out of our scope. So alkene formation, then Wasanalysis opened the ring. It formed dicarbonyl alkene to dicarbonyl. So chances of Wittig reaction. So Wittig reaction, phosphine ylide attacks the carbonyl. You end up with alkene there. If you read it nicely, you have 6 carbon containing terminal ester. Here which alkene will form is the stereoselectivity. Since the ylide is the stable ylide because negative charge attached with carbonyl, it form E alkene. The concept you have to learn here is Wittig reaction can be a part of larger molecule synthesis. Then the next reaction, the organic conversion reaction is given. You should find A and B here. Starting material is aldehyde, phosphine ylide, lithium aluminum hydride, ether at low temperature. In second set of reagent, you are having cyclic ether with tosyl acid. You should find what will be A and B. The conversion is simple if you know Wittig reaction. The starting metal is aldehyde, you are having ylide. So straightforward alkene formation. Since the electron withdrawing group present near the anion, it stabilizes the ylide. It forms E alkene. So first stereoselectivity here. Then lithium aluminum hydride you are using. It converts ester into alcohol. Then acidic condition you are using. Acidic condition promote the cation near the oxygen because lone pair can stabilize it. Mesomeric effect. End up with new unusual product. The concept you have to learn here is stability of the ylide dictate the final product. Then the next reaction. Here you have linear chain compound with one side aldehyde, another side ester. Phosphonium ion as the reagent with base. You should find what will be the final product. Here Ylide formation is the crucial step. First step will be abstraction of proton. The proton is weaker because it's near the cation, so it abstracted from the Ylide there. The Ylide is the unstable Ylide because it's near the electron donating group and it attacks the carbonyl. Which carbonyl react? Aldehyde or ester? Here aldehyde is more reactive than ester, so reaction happen with carbonyl of the aldehyde. So new CC bond forms, phosphine eliminates, you end up with final product. The concept you have to learn here is you should master the Ylide chemistry to master the Wittig reaction. Then the next reaction, you have linear compound with aldehyde, carbon tetrabromide you are using with phosphine, butyl lithium, copper sulfide and phenylazide you are using. You should find what will be the final product. This reaction involves different set of mechanism, different set of reaction. First step will be Ylide formation. Phosphine to carbene form the Ylide there because bromine is the good leaving group. Phosphine attacks form the Ylide. Then aldehyde you are using. Aldehyde and Ylide combine form the Wittig product, which is Wittig reaction leads alkene. 2 bromine you are using excess of butyl lithium, you end up with alkyne there. Then copper sulfate you are using, which remove the acidic proton there, H becomes Cu. Then acid you are using, acid with alkyne form the click reaction. Discussing click reaction here is beyond the scope. If you are interested, go and search separately what is click reaction, what are the advantages. Then the next reaction, here you have indole. Third position you have side chain aldehyde. Phosphine ylide you are using with ester substitution. You should find what will be the final product. Here phosphorus ylide is there. If you read down nicely with negative charge, you have the nucleophile which attacks the carbonyl there. Indole given as the distraction. Indole don't have any role here. So only negative charge and carbonyl interacts. You have new CC bond. Then phosphine oxide eliminates. You have alkene. Here which alkene will form? Anion is stabilized by carbonyl group of the Ylide. Stabilized Ylide form E alkene. So the final product stereochemistry is E there. The concept you have to learn here is you should always focus on the functional group in starting material. Don't get distracted by bigger molecules. Then the next reaction. Here you have carbonyl system with carbonyl ketone. You are using phosphonium salt with base and heating with 2 hours reaction. You should find what will be the final product. Here phosphonium salt is there. You are using the strong base. So chances of Ylide formation, base abstract the proton, form the negative charge, positive and negative nearby, which is Ylide there. Then Ylide is the nucleophile which attacks the carbonyl. Nucleophilic addition happen. So O minus phosphine nearby. Phosphine abstract the oxide. You end up with alkene. If you draw properly, you have alkene at the side carbon. The concept you have to learn here is phosphonium salt also can be a starting material which promote the Ylide with base. Then the final example. Here you have cyclohexanone with cyclic phosphine Ylide, osmium tetroxide and sulfuric acid. You should find what will be the final product. This reaction is interesting because it involves all the basic reaction. First step will be Ylide and carbonyl reaction form the Wittig product. Here you have two cyclopentyl group fused through alkene. Next step you are using osmium tetroxide which converts alkene into diol. Then sulfuric acid you are using. Sulfuric acid can remove the OH as the water. It form cation. The cation has to be quenched. So only pathway is ring opening, ring open, form the cation near the alcohol. Cation near the alcohol quench the carbonyl, end up with final product. We start from cyclic compound, end up with spiro compound. Then we will summarize what we learned. Wittig reaction means combination of carbonyl compound into Ylide form E alkene or Z alkene. How you find E or Z? That is stereoselectivity. If Ylide with electron withdrawing group, E alkene will form because it is stable, form the thermodynamic product. If the Ylide has electron donating group means the Ylide is unstable, very reactive. Kinetic products form stable Ylide, E alkene, unstable Ylide, Z alkene. More simply, stability of cation dictate the stereoselectivity, more particularly stereochemistry.